In the vast emptiness of desert worlds, science is pushing boundaries once thought impossible, transforming barren wastelands into thriving habitats. Imagine turning Mars into a green paradise or transforming the most desolate planets into new Earths. This isn't just science fiction, it's a race against time and nature itself. Join us as we explore the astonishing efforts to terraform the impossible, redefining what it means to create life where none existed before. The dreams and challenges of planetary transformation, transforming barren, desert-like planets into lush, Earth-like environments has fascinated scientists and science fiction enthusiasts alike for decades. The core idea involves creating a climate capable of supporting water in liquid form, fostering an atmosphere breathable for humans and other terrestrial life. One of the main challenges lies in establishing a sustainable cycle of greenhouse gases, which trap heat and raise surface temperatures to levels that can sustain liquid water. For planets like Mars, this means either importing or producing vast amounts of greenhouse gases, such as carbon dioxide, by leveraging surface materials or even releasing trapped gases from subsurface ice. Another major hurdle is the planet's initial environmental conditions. Many desert worlds lack magnetic fields strong enough to protect atmospheres from solar wind erosion, which results in the gradual stripping away of atmospheric particles. For Mars, scientists consider whether creating a magnetic shield or thickening its atmosphere could prevent this loss. It's a colossal engineering problem, one that involves not just modifying the planet's atmosphere, but also dealing with the crust, soil chemistry, and potential toxicities. The goal would be to eventually establish a stable, self-sustaining biosphere, which requires more than just adding water or heat. It demands understanding and manipulating planetary geology at an unprecedented scale. The practical aspects also bring about profound ethical and logistical questions. Employing large-scale geoengineering techniques on other planets involves risks that are hard to predict, such as unintended consequences on potential native ecosystems or future human settlers. Creating an artificially livable environment may require vast resources, technological breakthroughs, and patience that span centuries, if it's even feasible without catastrophic failures. Some thinkers argue that focusing on terraforming might divert attention from more immediate and pressing issues on Earth, yet others see it as a bold extension of human curiosity and resilience. Despite the formidable challenges, the dreams of planetary transformation keep inspiring innovative research and technological advancements. Experiments with bioengineering, for example, explore hardy extremophiles that could survive and thrive in hostile environments, gradually conditioning the planet's surface. Projects like NASA's concept of in situ resource utilization aim at using local materials to produce fuel, water, and breathable air. Not yet a reality, but each step forward fuels hopes that one day we might turn the impossible into reality, transforming worlds of dust and rock into new homes for humanity's future. Climate engineering, techniques, and limitations. Transforming barren planets into life-supporting worlds pushes the boundaries of current science and technology, especially when it comes to climate engineering. The fundamental challenge lies in altering an entire planetary atmosphere or surface environment to support water cycles, breathable air, and a stable climate. Techniques such as terraforming often involve introducing greenhouse gases to thicken atmospheres, stabilizing temperature ranges necessary for liquid water, or releasing volatiles trapped in planetary crusts. For instance, on Mars, proposals have included deploying vast factories to release greenhouse gases like CO2 or methane to warm the planet. But scaling such processes to planetary levels remains a tremendous logistical hurdle. One commonly discussed Earth-based method involves atmospheric modification through the injection of aerosols or reflective particles into the upper atmosphere. This approach, inspired by geoengineering concepts like solar radiation management, aims to reduce the planet's temperature by reflecting solar energy back into space. Although plausible on smaller scales and during specific climate emergencies, this technique faces insurmountable obstacles when applied to planetary terraforming. The unpredictable effects on the greenhouse effect, potential changes in weather patterns, and the difficulty of maintaining such interventions over centuries make it a questionable long-term solution. Moreover, such methods would require a precise understanding of planetary feedback loops, which remain poorly comprehended when scaled up. Another limitation emerges from the difficulty of removing or managing planetary nitrogen and carbon cycles. Earth's climate balance heavily depends on complex interactions within its biosphere. Replicating or stabilizing this process on a lifeless world involves not merely designing technological solutions, but also creating an entirely new biosphere. Introducing genetically engineered microbes capable of fixing nitrogen or producing oxygen is a theoretical possibility, but maintaining their viability and avoiding unintended ecological consequences is fraught with uncertainty. The timescales involved are lengthy, and the risk of causing irreversible damage to the nascent ecosystems or failing altogether looms large. Lastly, the entire concept grapples with fundamental limitations rooted in resources, energy, and feasibility. The sheer scale of engineering needed to warm a distant planet or to generate a stable, self-sustaining climate is staggering. Current energy sources and material supplies are insufficient for such endeavors, and the technological breakthroughs required are still in developmental stages or purely speculative. In essence, while climate engineering provides a tantalizing glimpse of how we might shape extraterrestrial environments, the complexity of planetary systems, their unpredictable responses, and the enormous energy demands set clear boundaries to what can be realistically achieved in the near future. Biological megastructures, creating sustainable ecosystems. Creating sustainable ecosystems within biological megastructures involves pioneering engineering and ecological principles to forge self-sufficient habitats on worlds that previously lacked the conditions necessary for life. This concept hinges on designing layered environments, integrating biomes, water cycles, soil regeneration, and atmospheric regulation within enormous artificial constructs that can sustain flora, fauna, and human life. Advances in biotechnology, synthetic biology, and environmental engineering enable scientists to develop organisms genetically tailored to thrive in controlled yet dynamic ecosystems, gradually stabilizing the environment. One of the central challenges lies in establishing closed-loop systems that mimic planetary cycles. For example, scientists are experimenting with bioreactors that cultivate microbes capable of fixing atmospheric nitrogen or breaking down waste to produce nutrients. These microbes can be integrated into soil layers inside domes or megastructures, creating fertile grounds for plants. By utilizing genetically modified plants engineered to withstand extreme conditions, researchers strive to develop resilient ecosystems that can survive and evolve despite the artificial environment's imperfections. For instance, crop species are being tailored to endure low light, variable humidity, and high salinity, mimicking the challenges faced on alien worlds. Another innovative approach involves creating layered biological architectures, urban-scale forests, algae farms, and microbial mats, designed to produce oxygen, sequester carbon, and purify water. These biological megastructures might include vertical farms with integrated microecosystems, which not only sustain human populations, but also contribute to the stabilization of the environment within the habitat. In some experimental setups, algae bioreactors have been integrated into living spaces, providing both oxygen and biofuel, while also offering a visual connection to nature. Such systems could serve as models for future ecological engineering, blending biological complexity with architectural design to foster sustainability from within. Ultimately, the goal is to develop ecosystems that are not static but adaptive, capable of responding to internal and external disruptions. Through continuous monitoring and genetic optimization, these biological megastructures could evolve over time, becoming increasingly resilient and self-regulating. While still largely experimental, these efforts represent a crucial step in transforming barren worlds into vibrant, self-sustaining habitats, each one a testament to the merging of biology, technology, and imagination in terraforming the impossible. Technological innovations and future prospects. Advancements in terraforming technology hinge on the development of sophisticated systems capable of transforming barren landscapes into hospitable environments. Innovations in atmospheric manipulation, for example, bring hope for enabling a balance of gases that support human life. Scientists are exploring the use of large-scale greenhouse gas emitters, potentially fueled by local resources, to artificially thicken atmospheres. These systems would need to be energy efficient and capable of sustaining the delicate equilibrium of oxygen, nitrogen, and trace gases. Technologies like electrolysis for oxygen generation and carbon capture for controlling greenhouse gases are already gaining traction in controlled environments on Earth and could be scaled for planetary applications. Efforts to modify surface conditions involve deploying a variety of robotic agents and materials. Enormous mirrors or orbital reflectors could redirect sunlight to warm the surface, trigger sublimation of polar ice caps, and release trapped gases. Meanwhile, continent-spanning pipes and reservoir systems could be used for redistributing water and creating initial freshwater sources necessary for microbial life. The introduction of genetically engineered microbes, designed to survive extreme conditions and produce vital gases, nutrients, or even soil, may serve as a biological foundation for long-term ecological development. These microbes can catalyze the breakdown of toxic minerals, produce oxygen, or fix nitrogen, progressively changing the planet's soil chemistry. One of the most promising directions involves harnessing renewable energy sources to power these complex operations sustainably. Solar panels, nuclear reactors, and even experimental fusion devices could deliver the immense energy needed for large-scale transformations. The idea is that, rather than relying solely on Earth-supplied resources, future missions could generate energy locally, reducing logistical burdens and environmental impact on Earth. For example, ongoing research into compact and highly efficient fusion reactors suggests that in the future, planetary terraforming efforts might become less dependent on early-stage Earth support, making the process more scalable and autonomous. These innovations open avenues for gradual planetary modification, reducing the risks associated with rapid or poorly understood environmental changes. Looking ahead, prospects like asteroid mining to extract water or essential minerals could support terraforming activities by reducing dependency on imported supplies. Furthermore, the fusion of artificial intelligence, autonomous robotics, and predictive modeling will likely streamline decision-making processes during the complex process of transforming hostile worlds. Machine learning algorithms could analyze vast datasets, predict environmental shifts, and optimize resource deployment in real time. As technology advances, the vision of converting desert worlds into vibrant, Earth-like habitats becomes more feasible, offering humanity a future where the impossible of transforming barren spaces into thriving ecosystems might someday become reality. Ethical and practical considerations of terraforming. Transforming barren planets into habitable worlds presents a complex web of ethical and practical dilemmas that challenge current scientific capabilities and moral boundaries. On one hand, the prospect of terraforming offers a tantalizing solution to humanity's growing resource needs and overpopulation concerns by potentially opening new frontiers for life. Yet, the very act of transforming untouched environments raises questions about humanity's right to alter nature on such a grand scale. For instance, introducing Earth-like conditions to Mars or exoplanets could irreversibly erase native ecosystems or potential indigenous life forms that we haven't yet discovered, making the act of terraforming a form of ecological theft. Critics argue that we should prioritize preserving existing ecosystems on Earth before considering the manipulation of other worlds, emphasizing that the risks of irreversible damage or unintended consequences could outweigh the benefits. Practicalities aside, the scale of engineering required to sustain a stable, Earth-like atmosphere or climate on a desert planet is monumental. Technologies like releasing greenhouse gases to thicken atmospheres or introducing genetically modified extremophiles to kickstart biological processes are still in experimental stages. The economic costs alone are staggering, with estimates for a single Mars-scale project running into trillions of dollars, raising serious questions about resource allocation. It's also worth considering the long timeline. These projects could take centuries, during which unforeseen environmental or technological challenges might derail efforts entirely. The sheer unpredictability of such engineering endeavors makes them risky, especially when the planet's unique geology or radiation environment could sabotage terraforming attempts. From an ethical perspective, the potential for terraforming to become a form of cultural imperialism or colonialism is significant. As humans venture into space, the question of consent becomes tangled. Should we have the right to impose life and ecosystems onto worlds that might be considered autonomous or even sacred in some hypothetical future worldview? The notion of planetary stewardship involves a balance. It assumes a responsibility to avoid harming or overly disrupting extraterrestrial environments. There's also the issue of prioritizing Earth's thriving ecosystems versus the potential benefits of colonization. Some argue that humanity's focus should remain on repairing and conserving our home planet rather than risking everything on speculative off-world engineering projects. Preserving the integrity of untouched worlds might be viewed as an obligation rooted in respect for the universe's natural diversity, rather than merely a hurdle to be overcome in our quest for expansion. As we've seen, transforming barren, lifeless worlds into thriving ecosystems is a monumental challenge, one filled with innovation, perseverance, and a touch of daring. From the detailed engineering concepts to the ambitious experiments, each step brings us closer to what once seemed impossible. It's a story of human ingenuity pushing the boundaries of what's feasible, fueled by the hope of expanding our horizons beyond Earth. If this journey piqued your curiosity, there's so much more to explore. Imagine what future breakthroughs could unlock: new ecosystems, thriving colonies, perhaps even new homes. This is just the beginning, and First will be right here to bring you along on every discovery and setback. Stay tuned for upcoming videos that dive deeper into the science, the risks, and the incredible potential of terraforming. If you're as fascinated as First and by turning impossibilities into realities, don't forget to subscribe, share your thoughts in the comments, and join the conversation. Together, we're dreaming big and reaching toward a future where the impossible might just become our new normal.